Hello, welcome. So this is, let me just adjust, there's the camera. This is the recap for this week's stream, and this week we started with a puzzle from the previous week, which was why was everything so weird? So there was something absolutely going wrong in the results, and I figured it out before the stream. So last week on Friday, before going home for the weekend, I decided to just clean up every intermediate file and just leave the process running from scratch. On my computer without, normally I'm running things on my computer, I'm doing a lot of other things at the same time. And so over the weekend it just ran. And when I came in, everything looked good. The artifacts, the weird puzzle was gone. Everything looked exactly as it should. And so it spent a little bit of time on Monday, and then I actually quickly realized what could go wrong. And then it took me a little bit more time to figure out exactly how to trigger it. But so here I'm just going to jump directly to the punchline, right? So here's this little Python script, very short, run checkm2. This is what we use to run checkm2. So we import subprocess here. So this is actually a version of the inputs, just a bit shorter or fewer bins, and then we call subprocess check call, and then we have this conda run in a other environment. We run checkm2, and so let me do this. I do this. If I run top here in another, you can see here's OBS. This is the recording software, and now it's running Prodigal, which is the first step in checkm2. If I press Ctrl C, Prodigal is gone, and it's now just running OBS and XOR, right? So far so good. So now I'm going to do this again, and I'm going to let it run a little bit longer, and so it's going to run. So again, see, checkm2 is running. The first step, it's going to call Prodigal to predict genes in all of these genomes. And once it does that, it's going to run Diamond. And I think if I interrupt it, and we'll test it here, if I interrupt Diamond at that stage, or if I press Ctrl C at that stage, it will actually not interrupt Diamond, and checkm2 will continue to run, and it will just keep going. And then what I think happened is that I did something like that where I was running checkm2 indirectly through jug, which then calls conda run, which then calls checkm2, and probably at some point for some reason maybe I had a meeting where I wanted Zoom to work smoothly, or I wanted to run something else. I pressed Ctrl C and then later restarted it, and somehow this probably led to two versions of checkm2 running at the same time and overwriting each other's intermediate files. So here you can see that you have Prodigal running, and you can see here. So where am I? Okay, sources. So this is the output from checkm2, and so you can see, right, so there's a log file, the outputs from Diamond, and then all of these files from running the different mutated versions. And if two versions of checkm2 are running at the same time, and each it can easily happen that one of them is still working on something, the other one starts running, and now it thinks it has finished, but for some reason it hasn't. So it ends up working with partial files. So I've talked about before that it's very, very common that programs write these partial files as they go along. Normally that's fine, but it can lead to these issues. So let's see how we're going. So this might take a little bit longer for us to be able to trigger this, but it will. It's a little bit finicky exactly how to trigger the issue. I think sometimes I press Ctrl C and it keeps going. Sometimes I press Ctrl C and it so let's try now. If I press Control C, does it keep going? Check M2. Yeah, see, all right, there it is. I don't know exactly the conditions to trigger this, but right now, so what happened was, yes, so I pressed Control C, and somehow in this stack of things that running on top of each other, check M2 was happy to keep going with Diamond. And so this is what I think happened. So not sure exactly, I'm gonna now kill it. Not sure exactly what to do about this. This is actually a probably pretty complicated issue to debug all of the intermediate steps, but I'm going to be a little bit more careful in the future. So let's just clean up these things that were just there for us to. Yes. So now we're back to a clean slate. This was just there for me to show you what was going wrong, right? So what did we actually do this week then, after we've solved this mystery? Now everything looks good. So now we took this plot check M2 script that we had before. I'm gonna do this little bit of magic code. And there it is. So this is what we had before, but now we've turned it into a loop where we can import and get. So this is what we had before for E. coli, right? And now you can see it looks exactly the same as before. It still has this weird effect at the end. I mean, this is actually a ridiculous number of mutations, to be honest. We should have and often we're then cutting it here. We probably shouldn't even have computed so much. But as we're playing around, this happens. So we turn this into a loop, and we generated them all for the different. So you can see they all kind of look the same. In that example here, staff arrays is a little bit different. You have this little effect, this little bump, but they all kind of look the same. Where up below 1,000 mutations, you still see check M2 pretty even, and then the average gene size going down. Right. So the next thing we played around with was, okay, how this was part of looking at the check M2 outputs, trying to debug. So far we had looked at the quality report, which is the final results. So this is it, right? This is it. Right, so with 50 mutations, 100% completeness, 150 mutations, 99.9% completeness. But this comes from check M2 looking at the outputs of Diamond. So we looked at I had spent a little bit of time trying to understand this better. So first of all, most of these, they have these two Diamond results 0 and Diamond results 1. So these are actually completely the same. Just that if the files are very big, check M2 is going to split it up. But then here we have that. So this is some protein annotated to this, which has this KO, so this orthologous group. And so we could turn this, so we could load this as well. So we load these outputs. And so we need to do a little bit of manipulation here to get the things to look exactly how we want. But in the end, what we can do is use this data to get here. It's here. Let me just bring that. Yep, there it is. So we can use this data. So here what we're doing is, so we load the tables, then show you again. So you can see, so this is the format that checkm uses. So this is the bin name and then this omega symbol, and we can and we can see, so we can use here, so we split at the omega. Actually, in the meanwhile, I realized that I can actually type, I actually don't even know what I installed to get this, but I can, if I do this, omega, I can get this. Look how cool this is, right? Very nice. Anyway, so that's I don't even know what to install. That's control dot space, and then this shows up animals nature. So it's like koala. Here's the koala. No, I didn't mean to. Yeah, koala. There it is. Anyway, complete sidetrack there. But all right, so we're back to. So we split by the query by the omega symbol to get this. So to get the bin name, and then we split the result by the tilde to get the KO. Right, and now we can get the groups, and let's say that with 0 mutations, this is perfect. So this is the unmutated KOs, and then we have false positives and false negatives, right? And then we can see. Right, so here, look, the scales are different. So I actually on the stream I first messed this up, but in the end this is correct. So the false. So yeah, so the. Okay. Oh, maybe it's. I'm again confused. Yes. Okay. Yes. So the green is the false negative. So that means the KOs that are missing. So you can see that as the number of mutations grows, it goes up by quite a lot. So this is thousands of KOs. Whereas this orangey color, this is the number of false positive KOs, and you can see it's much smaller. So the scale here goes up to 80, and there it goes up to 2,000. So we can look a little bit more. Just limiting ourselves to low thousands of mutations, and you can see again the number of missing KOs. We have it. So about 1,000 mutations, that might, 1,000 something mutations, that might be a reasonable-ish number. But we already have 1,000 missing KOs, which is actually quite a lot. And whilst the number of false positives is still in the low tens. So this means we could look a little bit more into what are the false positive KOs, where do they actually come from? But I'm not going to be doing that. I think we're gonna keep exploring this next week. So we did this. So we did this for all of them. So we put in this. So here. No, this is the completeness. Yeah. So we did this for all of them, and they all look the same in terms of this pattern of a quick rise in the number of missing KOs. And then a corresponding rise in the number of false positives, but the scales are not the same. So if they were put in the same scale, this line would basically be down here at the bottom, right? So that was it. So we managed to make a fair amount of progress in understanding this issue. And yeah, so next week we'll probably keep going, trying to understand what's going on. We'll probably be spending the next few weeks still sort of exploring and sort of trying to play around with the data, trying to gain intuitions, just thinking about it, and then maybe by July and after I get back from my travels, we'll have a break for the travels. I'll be ready to then transition from this more sort of random exploration, random walk mode into trying to figure out a specific direction to go to. All right, so yes, please subscribe. I'll be posting this on the mailing list as well. I'll post everything there. We're happy to chat on Discord, and yeah, I'll be posting a couple more videos still this week on other stuff that we've been doing as well in the group. So that will be in the main channel. So yeah, talk to you soon. Bye bye.